Hey everyone, welcome to Professor Long's Lectures on Anatomy and Physiology. I'm Professor Bob Long. This video is intended for those students that are enrolled in my Human Anatomy and Physiology 2 course at Del Mar College during the summer semesters. Okay, these videos are somewhat timeless though, in the sense that anyone can watch them at any time and learn some information about anatomy and physiology. As you guys know, we're in the coronavirus or COVID-19 shutdown. My face-to-face courses have been converted to online, so that's the reason that I developed this YouTube channel. I'm doing these videos so that my students can still get the instructional delivery. I'm an old school lecturer, so I'm still doing everything writing on a board. I, as a neurobiologist who studied memory and learning in the brain, have a great deal of knowledge of how memory and learning works, and I know that when we use our hands to do things, we learn better. So I like for my students to write and draw along with me. If I show you completed images, you don't learn as well. You can learn, but it's deeper ingraining in the system when you are actually doing something along with me. So hence the style. This is lecture number, it's supposed to be lecture number 3 in my sensory physiology series. But in the last video, for some reason, the camera stopped for a fraction of a second and then started up again. We've been covering the general senses and comparing the general and the special senses. If you're following along in my note set, I'm on the bottom of page 6 for those of you who are in my class. We're going to be talking about the general sensory receptors, the different modalities and the types of receptors. The first one that's listed is nociceptors. So we're going to be talking about nociception. And if you read in the note set, there's some spaces for you to write some stuff in. The nociception is the detection of pain, or another way we say it is analgesia. Anytime you see analgesia, it refers to pain. So someone who is taking an analgesic, I mentioned this before, but you should know this. An means not, or anti, against. Analgesic is pain. So an analgesic is a pain med. If someone is experiencing what we call hyperalgesia, then that's someone who's super sensitive to pain. You know, every little thing that hurts, the normal person could tolerate. Someone with hyperalgesia experiences an extreme response, and therefore they're very, very sensitive to pain. Okay, they have an overreaction to pain. Now, when we talk about the nociceptors themselves, nociceptors, pain receptors, are considered to be what we call free nerve endings. What that means is this: in some of the general senses, the neuron out in the periphery can either be a free nerve ending, or the end of the neuron can be coiled up with some connective tissue and have tissue around it. Pain receptors, nociceptors, are free nerve endings. They don't have a lot of connective tissue surrounding them. Okay, they are located in a number of regions that we find in the body. One area, these are some of the areas where we find these receptors. They're very high up in the dermis, very close to the epidermis. Okay, right at that border. So if you remember our study of skin, the uppermost layer of the skin would be called the epidermis, and then the layer below that with a lot of connective tissues in it would be considered the dermis. Okay, well, some of our nociceptors are located very, very high up in the dermis. The axons will come up and sometimes sit right underneath these little pockets, or very close up, and sometimes extending right up to the very lower levels of the epidermis. That makes sure that when we hit them, we don't have to do a lot of damage to the body to reach them. They're very high up in the dermis. Okay. Another location for nociceptors, they're found very abundantly in our skin. They're found in the periostea, or the periosteum of bone. So when you fracture a bone, you tear that periosteum, and the nerves that are in that periosteum get torn, and those pain fibers send a signal to your brain. It's very painful. Trust me, I know. I've broken a lot of bones. They are found in the walls of blood vessels. When you cut a blood vessel, you know it. It hurts. It's very painful. And they can be found in joint capsules and muscles. So whenever you tear a muscle, it's painful. And whenever you damage the joint or the joint capsule, it's pretty painful. So we find them in these 4 areas in great abundance. There are also a lot of pain fibers in the internal viscera, like having a stomach ache or when you're feeling pain in the abdomen. One thing to note about the internal pain receptors, the ones in the abdominal cavity or surrounding a lot of our viscera of the body, there are fewer of those and further between with large receptive fields. I mentioned this in some of the last videos, but when we are feeling pain internally in the abdomen, we can't pinpoint the exact location very often. We can give a generalized area. If you're feeling pain in your knee, you can point exactly to which part of the knee or the knee joint where you're feeling the pain. But in the abdomen, there's so few of the pain receptors and they're so far apart, they have large receptive fields, makes it difficult to pinpoint the location of the pain, okay? Now, when it comes to nociceptors, they can respond to 3 different types of stimuli. They're sensitive to 3, specific types of stimuli. One of them is what we call physical or mechanical distortion. So, this would be like if you stepped on a nail and you cut the pain receptor, or if someone pinches or twists your skin. So that physical damage or mechanical damage will set off certain pain receptors. They can respond to extreme temperatures. So if you ever stuck your hand in an ice chest, looking for a soda while you're floating a river, because you drink Cokes when you float a river. If you stick your hand in that ice chest, man, it starts to hurt. It gets painful. And extreme heat will cause a burning pain, okay? And there are specific chemicals, usually extreme pHs. Something very acidic or very basic will set off a pain sensation, okay? Now, in really extreme pain, all of these get set off. Sometimes you feel, it's described as a burning sensation. And that's when someone's really feeling a whole lot of pain. Okay. One of the things that's not listed in the note set, but I want to mention to you, is that one of the neurotransmitters, there was a neurotransmitter discovered that's utilized by a lot of pain fibers. That neurotransmitter, by the way, is called substance P. Makes it easy to remember, substance P for pain. So that's one of the neurotransmitters utilized in our brain when we're interpreting pain. Something interesting to note, our pain fibers or nociceptors are tonic receptors, meaning they're always releasing neurotransmitter. They can release more or less, depending on types of stimuli. But when they adapt, we actually undergo, in some instances, central adaptation. So the pain stimulus can still be there, but somewhere along the sensory pathway, we filter it out. I think I said in a previous video that they're like phasic receptors, that they're either on or off, and that's not 100% accurate, but nonetheless. So finally, pain fibers can respond. There's 2 different types of pain fibers. We call them type A fibers or axons, and there's type C fibers. So you should know the difference between the 2. Type A fibers do what we call fast or sharp pain. Very often this is the pain at the moment of injury. If you were, say, playing tennis and you went to hit a shot and you twist and you hurt something in your knee, that information gets communicated to your brain before you complete the motion so that you can remove yourself from the painful stimulus. So we call that a very fast or a very sharp pain. It's usually on the moment of injury. And I'm going to erase type C for a second and rewrite it. One thing we know about type A fibers and type C fibers is this. I had to move that because I needed to put some information in here. For type C fibers, they tend to do what we call, they do what we call slow. Man, I just can't write right now. And I don't want to start this video over. You guys have no idea how long it takes to make these videos right. So I'm going to deal with some minor issues here. But for type C fibers, they do what we call slow pain, or what we would call a dull ache. Very often, this is not a pain that you feel at the moment of injury, but you feel this long after the injury. It's sort of a soreness and some aches that set in to remind you, hey, your knee's bad, don't go try to run a marathon or something. They remind us to keep off of it so that we can let the body heal. Now, a few characteristics. Type A fibers actually fire very fast action potentials. If you remember in part 1 A&P, we talked about 2 ways that we can increase action potential velocity. One of those ways is to have a much larger diameter axon. If you were to just look at the number of ions, like sodium ions, that could flow through this, bringing a certain amount of voltage, millivoltage or charge down the axon, I can have a lot greater voltage flow down this axon than I can flowing in this one. Okay, so one thing we know about type A fibers is they have very large diameter axons compared to type C fibers. That allows a faster flow of action potential. These have a smaller diameter axon. Also, type A fibers tend to be myelinated. If you recall about myelination from part 1 A&P, one of the things we know about myelination is these cells called Schwann cells in the PNS anyway, in the CNS it would be called oligodendrocytes, wrap around the axon and insulate it, and they're interrupted by nodes of Ranvier. So the axon is actually traveling in here. All of the sodium ions that need to flow into the cell through ion channels to conduct that action potential can't access the axon here. But if enough of these ions in this area will diffuse through, passive diffusion and hit some of the voltage gated, some of the voltage gated channels at the node of Ranvier, when that opens, I can let a ton of ions flow in, and the ions will look like, or the voltage will look like it jumps from node of Ranvier to node of Ranvier. So these undergo saltatory conduction because they are myelinated. Where type C fibers tend to undergo what we call continuous conduction because they are unmyelinated. So I didn't write all that down, but you should know type A fibers have large diameter axons and are myelinated, so they undergo saltatory conduction and they send very rapid action potentials. Type C fibers send much slower action potentials because we know the pain, the injury happened, we just need to be reminded over time. So they have smaller diameter axons, they are unmyelinated, they undergo continuous conduction. Okay? Now, if you're following along on the note set, 2 things that we can add to our understanding of nociceptors. And again, these are just very basic, fundamental descriptions to get a fundamental understanding. There's a lot more to this, but we could spend an entire semester doing nothing but pain physiology. Now, there's 2 different types of pain that we can talk about. One I mentioned in a previous video called referred pain. Referred pain is pain felt in another part of the body or interpreted in a part of the body that is not the location of the stimulus. I talked about having a heart attack and people having pain down their left arm. So there are some types of pain where we get what's called referred pain. You detect the pain in a location of the body that is other than the location of the stimulus. And then there's one that's called phantom pain. As you know, a phantom is a ghost. So in phantom pain or ghost pains, you're experiencing pain in a limb that's been amputated. Your hand may not be there anymore. If someone had their hand so badly mangled and the nerves were so badly damaged that it continually sends pain, there are some instances where that limb can be amputated to remove the painful stimulus if that limb's not usable. Because those axons are still sometimes sensitized and fire, you can feel pain, and because our brain interprets the information based upon the labeled line on which it arrives, you think you're feeling the hand and the pain in the hand even though it's been amputated. So we call pain from a limb that's been amputated a phantom pain. Now, another type of neuron that's very similar to pain receptors are called thermoreceptors. As far as their construction, thermoreceptors are very similar to pain receptors. Thermoreceptors detect rapid changes in temperature. A thermometer checks your temperature. So thermoreceptors do rapid changes in temperature. They're also located in the dermis. They're free nerve endings. And extreme temperatures can cause them to fire pain signals. Now, the hot receptors and the cold receptors that we can see are actually, histologically, they look almost identical. They look like twins. The difference is, if I have two thermoreceptors, a hot receptor and a cold receptor, if I increase the temperature, the hot receptors will fire, the cold receptors won't. So some are sensitive to increases in temperature. The cold receptors will respond to decreases in temperature. So if you jump in a cold swimming pool, the cold receptors fire and you start to feel that coldness. If you jump into a hot tub, the hot thermoreceptors will fire and you'll feel the warmth. Now, thermoreceptors are pretty fast adapting, when they do adapt, you no longer feel that sensation. For example, if you jump in a cold swimming pool and you swim around for a while, someone else wants to jump in. They say, no, it's too cold. You say, just jump in. You'll get used to it. Well, that's a type of adaptation. You're adapting to the change in temperature. Okay. I'm not going to talk much more about thermoreceptors. Just know that hot and cold receptors are different from each other in their histology and their physical appearance. But there are some that respond to rapid increases in temperature, some that respond to decreases in temperature. And then we're going to get to all the different tactile receptors. Tactile receptors do touch. There's a whole series of tactile receptors, although some books don't classify them this way. So when it comes to the tactile receptors, some of the tactile receptors are going to respond to what we call fine touch. Okay. One of the ones that's listed, by the way, first, there's free nerve endings. Well, we've already talked about the free nerve endings. Free nerve endings don't have any connective tissue surrounding them, and there are two types. There are the nociceptors and thermoreceptors that we just talked about. Okay? We don't need to talk about those anymore. There's one called a root hair plexus. A root hair plexus, and many of these tactile receptors are found in the dermis of the skin. When we look at hairy skin, wherever a hair follicle sticks out of the skin, these receptors actually come in and coil around the base or the root of a hair follicle. If you stimulate or brush the hairs on your arms, that will trigger these. So the root hair plexus is wrapped around the base of a hair or a hair follicle. Now, if I have several hairs sticking out of the skin and I have 3 different receptors here, if I trip them in this order, it will tell me which direction something is moving across the surface of the body. If I trip them in reverse order, then it tells me something is moving in the other direction. So root hair plexus wrapped around the root of a hair follicle. And one of the things they can tell us is the direction that something is moving along the body based on their firing patterns. Okay. Now I'm going to try to peek at my notes on occasion. I don't actually have any notes written in my note set. If you ever look at it, it's blank. But I do peek at it from time to time, even though I've been doing this forever. I'll look down at a page simply because I want to try to do these in the same order that they're written in the note set so you can follow along. Now the next type of receptor that's listed is called a Merkel's disc or Merkel's corpuscle. A Merkel's disc is surrounded with some connective tissue. There's some wrapping around them. And Merkel's discs do what we call fine or light touch. One of the differences between Merkel's and Meissner's, a Meissner's corpuscle, both of these do fine touch or very light touch, okay? Like someone caressing your skin. One of the differences is these are found in hairless skin, where the Merkel's are found in hairy skin. They both do light touch, but there are certain parts of the body where we don't have any hair. For example, the palms of your hands and the soles of the feet have no hair on them. So we find Meissner's corpuscles there. They do very, very fine or light touch. We also don't have any hair on the actual surface of the eyelid itself. If you close your eyelids and look at them in the mirror, you have very fine hair all over your face and over most of the body. But on the actual eyelid itself, there's no hair. Something's going to touch your eyes. If there's a bug crawling, you want to feel it, that very light touch, and protect yourself. We don't find any on the lips or the labia. There's some all around it, like in a mustache or a goatee, but not on the actual lips themselves. So they're very, very sensitive to light touch. The actual nipple itself that sticks out of the areola usually is hairless, and they're very sensitive to fine touch. And the actual genitals themselves, the glans penis or the head of the penis and the clitoris itself, don't have any hair on them, nor the labia or some of the folds of skin around that. That makes them very, very sensitive to fine touch, okay? Puccinian corpuscles, also called lamellated corpuscles, and Ruffini's corpuscles. A lot of these are named after people that first discovered and described them. A lot of books now are changing those names. They want to get away from the personal names and come to these scientific terms, but a lot of them are still listed this way. Puccinian corpuscles and Ruffini's corpuscles, these both do deep pressure, okay, and some vibration. Puccinian corpuscles and Ruffini's corpuscles do a slightly different deep pressure, especially the Puccinians, which do a lot of vibration in our skin. So if you were, you know, the new massage guns that athletes use to massage themselves, a lot of that vibration and deep pressure is being detected by Puccinian corpuscles. Ruffini's also do some deep pressure. One of the ways I remember them is M&M are fine, like M&M's, a fine chocolate candy, although they're not that fine of a chocolate, but they're delicious. But M&M, Meisner's and Merkel's do fine, okay? Puccinians, the P and R are rough, okay? So they do rough pressure or deep pressure. It's kind of an easy way to remember those. You can look up some more detail on those if you like. I'm not going to spend much more time on them because we could, like I said, we could spend all day, all semester on this chapter. For proprioceptors, there's two different proprioreceptors listed. Proprioreceptors, as you know, detect proprioception or body position. Okay, they tell us a lot about our body position in space. And this is part of our muscle memory. There's two different types of proprioceptors are found in two different locations. There's one called, I'm drawing a blank, the muscle spindles. Yeah, I couldn't think of the word, sorry. Muscle spindle fibers. These are going to be found associated with skeletal muscle, and they tell us about the tension and stretch in a muscle. So muscle spindle fibers tell us about tension and stretch in a muscle. And then the other one are called Golgi tendon organs. These are found in the tendons that attach a muscle to a bone. They'll tell us about the stretch and pressure or pull. Tension is the word I'm looking for. They tell us about the stretch or the tension in the tendons that the muscles attach to. Okay, so both of these are telling us about, you know, tension and stretch and muscles, or in tendons that attach the muscles to the joints. So they tell us about our body positioning and joint positioning. That's about all I want to say about those. When it comes to the next type of receptor, we talk about baroreceptors. Now, I mentioned all of these before in the first lecture, but baroreceptors detect pressures, okay, changes in pressure in some organs. So, when it comes to the baroreceptors, you certainly would find them in things like the digestive tract, the urinary bladder. In the digestive tract and the urinary bladder, they tell us when we're full so that we either stop eating, or you know you have to go urinate, or you know you have the urge to defecate. So there's pressure receptors in the digestive and urinary tracts that tell us about those pressures. But one of the things we haven't covered yet is the cardiovascular system. But coming out of the left ventricle, so your heart is divided into 4 chambers. The bottom left chamber is called the left ventricle. The largest pipe that's going to deliver all the blood to all the tissues of the body is going to come out of this, and that pipe is called the aorta. The aorta comes out of the heart, arches back, and then runs down the abdomen and has branches that feed blood to all your organs. 2 of the major branches coming off the aorta. The first one, as it comes out of the heart itself, it's called the brachiocephalic, and it's going to have a branch that goes up to your head. On the other side, we don't need this little extension, but these 2 arteries that are coming up towards the head are called the carotid arteries. The aortic artery, or the aorta, and the carotid arteries have little areas in them where we find some receptors. One set of receptors, these are called the carotid bodies and the aortic body. The carotid bodies and the aortic bodies have baroreceptors. When our heart has to undergo sympathetic stimulation and it contracts under great force, the blood shoots out and puts pressure on the walls of these vessels. If blood pressure rises too high, then some of the very tiny branches downstream called capillaries and arterioles can rupture. We call those vascular accidents, and in some forms they're called strokes. If you ruptured blood vessels in your brain, it would be called a cerebrovascular accident. If you rupture some in your heart, then they could be cardiovascular accident. And if they're in the lungs, they can be called pulmonary vascular accidents. And when you rupture those blood vessels, no more blood can flow to the tissues on the other side of the rupture. And in the brain, that causes neural deficits and damage to neurons. So our body has a way to measure our own blood pressure. If it drops too low, we can send signals to the brain or the heart and increase the force of contraction and the rate of contraction to make sure that we're delivering adequate oxygen and glucose and nutrients to our cells. If blood pressure rises too high, that can be dangerous, so we have mechanisms that can feed back and lower heart rate and blood pressure, sympathetic and parasympathetic activation of the heart. So the carotid bodies and the aortic bodies have baroreceptors that are monitoring our blood pressure. Okay? Now, one of the last things I want to do before we start moving into the special senses is I want to talk about chemoreceptors. Okay? Chemoreceptors, there's two different types of chemoreceptors. There's chemoreceptors that monitor the internal chemical environment. They're part of the general senses. And then we have external chemoreceptors. They're going to be part of the special senses. For the internal chemoreceptors, they're monitoring concentrations of a lot of the nutrients and ions in our body. For example, sodium and potassium play a huge role in action potentials. The chloride ions play a huge role, and so do calcium ions in our physiology. So our body is monitoring our salt levels in our blood and kind of at the same time monitoring water levels or hydration. For example, if I take a bucket of fluid, some pure water, and I dissolve a whole bunch of salt in here, sodium and chloride and potassium, and I dissolve some sugar in here. Now I can be measuring the concentration of salt and sugar in this container. If I could tap off some of the water and drain it so that I lower the volume of water, but I do not alter the concentration of the ions. I don't have any ions that exit here. Then what essentially happens to the salt and the ion concentration is I've increased the concentration of salts and sugar by dehydrating myself. So under dehydration or overaccumulation of salt or sugar, we can alter our body's concentration of these substances. Well, the internal chemoreceptors are monitoring this. We have some of those internal chemoreceptors in the hypothalamus of the brain, and they're monitoring some of these concentrations. We also have oxygen receptors in the carotid and aortic bodies that are monitoring oxygen and carbon dioxide and pH. When we don't get enough oxygen to our tissues, we're also not ridding carbon dioxide. Carbon dioxide and water can enter into a chemical reaction and form carbonic acid, and then that dissociates and makes your pH of your blood become altered. If blood pH starts to drop too low, becomes acidic, then our body can be triggered, and there's a way that we can trigger mechanisms to restore that. We're not going to talk about that at this time. We will when we do respiratory system and urinary system. There's respiratory acidosis and metabolic acidosis. If the blood pH becomes too basic, then you're in what's called alkalosis, and we still need to trigger the brain to fire those mechanisms to restore the pH of the body. So the internal chemoreceptors are monitoring ion concentrations, nutrient concentrations, and sometimes oxygen and carbon dioxide concentrations or blood pH to make adjustments to keep us in our homeostatic range. Okay? So that's all the general senses. So we've done 3 videos so far. We've done an introduction to the sensory system and a comparison of the general senses. The second video was a continuation of that. It was supposed to be one long video, but fortunately the camera broke it up. For some reason it worked out to our advantage. And now we've done all the general sensory modalities. This again was a very brief and rough introduction. You do need to go in and read the chapter of the book and read up a little bit more about these. Now, I'm going to cut this video here, and then we'll move on to the special senses, and we'll do several videos on the special senses because there's a lot to cover. So, I hope you learned something. I hope you had as much fun as I did, And I'll see you on the flip side of the next video. Thanks for watching.